So in the last video, we determined the end behavior, right? When we zoom out, we can look at the end behavior when we look at plugging in really big numbers and really small numbers. Now we're going to talk about the zoomed in part, the turning points. How many maximum and minimums can I have? All right, and so again, it matters, and this time it is the degree of the polynomial that tells me, and I can only guess at how many I could possibly have, and I can also guess at how many times I cross the x-axis. All right, so how many local extrema are possible, peaks and valleys, all right, local max and mins, turning points, when I change from increase to decrease and the other way around, decrease to increase. And so a polynomial of n degrees can have at most, so this one's not quite as exact as the end behavior. I know exactly the end behavior using the leading term. This one, all I can do is make a prediction. I can have at most n minus 1 turning points, where n is my degree. All right, so we can have up to, so if it's degree 3, I can have at most 2 turning points. If it's a degree 2, I can have at most 1 turning, and that should make sense. A degree 2 is a quadratic. It only has 1 turning point, right? The vertex. I can also tell using the degree how many times I could possibly cross the x-axis. Right? And it's the same. As many turning points as I could have are as many times as I could cross the x-axis. And so I can have at most x-intercepts. And remember, x-intercepts are the 0. So if I have a degree 3, I can have at most 2 zeros. Or sorry, no, n. If I have a degree 3, I have at most 3 zeros. If I have a degree 2, I have at most 2 zeros of a degree 1. And it should make sense. You can use the 1 degree and the 2 degree. Right? If I have a line, which is a 1 degree polynomial, it crosses the axis 1 time. If I have a polynomial, a quadratic, right, a U-shaped graph, it can cross up to 2 times. It can bounce off of it, have 1 x-intercept, or 0, right? So it can have at most 2. A 3 degree could have at most 3. Again, 3, 2, 1, or none. All right, and so based on the degree, I can make a prediction. Now, it doesn't tell me exactly how many they have, but it tells me all of the possibilities. All right, that's what it does. So it narrows it down a little bit. So it's not quite as good as the end behavior. So we're going to look at the most common graph. So we're going to start with all the different types of degrees, and then we're going to talk about end behavior again as well. All right, so for our quadratics, the common function, the quadratic. So it's a degree 2. Right? And so based on the fact that I know it's a polynomial of degree 2, it's a parabola. It opens up if my a is positive. It opens down if my a is negative. It can have at most 2 zeros. Right? So it means it can have 2 x-intercepts, 1 intercept, or none. And it can have 1 turning point, all right, called the vertex. That's the possibility. And then the end behavior, well, it goes the same direction. If it opens up, right, a is positive, both sides are shooting off to infinity. If it opens down, a is negative, both sides are shooting down to negative infinity. And so these are the possible graphs, right? I have no x-intercepts. I have 1 x-intercept. I have 2 x-intercepts. All of them have 1 turning point, which is either a max or a min, right? My vertex is my 1 turning point. And then both sides are shooting in the same direction. So if it opens up, both sides are shooting to my infinities. If it opens down, both sides are shooting off to my negative infinities. All right, and again, it just depends on that a term at the front. Cube. So a cube would be just a cubic function, has a degree 3. Since it's degree 3, it can have 3 x-intercepts or fewer. So it can have 3, 2, or 1. And it can have at most 2 turning points. That's it, 2 turning points. It doesn't have to have 2 turning, but it can have at most 2 turning points. And since it's an odd degree, it has opposite end behavior. So if a is positive, it'll go to negative infinity to the left, and it'll go positive infinity to the right, right? So it shoots the same way it's supposed to go. It goes positive when you plug in positive, negative when you plug in negative. When I have a negative number up front, it does the opposite, all right? It goes to positive infinity on the left, negative infinity on the right. Since we're moving in opposite directions, it does have to cross the axes at least one time. So it's never going to have the 0 case. It's always going to have 1 to 3 intercepts because it has to cross it because it's going off to an infinity on both sides, positive and negative. So it has to cross it at least once whenever it's an odd degree because it has opposite end behavior. Alright, so here's a couple of examples. These are all cubic functions. So this is an example of where it has 3 x-intercepts. Right, and so it would have, based on the shape of the graph, my A would be negative in the first case. Right, and the second graph, my A would be positive. Alright, so in this graph, because of the shape of the graph, I know my A is negative because it's shooting off in left side's going off to negative infinity, right side's going off to positive infinity. It has 2 turning points. Right, it's got a minimum and a maximum, localized max and min. Alright, this one only has 1 x-intercept. Right. It's going off to negative infinity to left, positive, so that means A is positive, right? It's shooting off to positive infinity where it's supposed to on the right side, negative infinity to the left side. There are no turning points in this case. Alright, the next example, it crosses it twice, right? It has 2 x-intercepts. So there's 1, 2, 3 cases. 2 x-intercepts. It also has 2 turning points. All right, it's got a minimum and a maximum, and it's shooting off to infinity on the right, negative infinity to the left, so that means that leading term A had to have been positive, right? Because it's shooting off in that direction. All right, that's the cubic case. All right, so next we're going to look at the 4th degree polynomial. All right, so the 4th degree polynomial is the next one. Right, so a 4th degree polynomial, a quartic function, which we don't usually call, we just usually say a 4th degree polynomial. All right, so my 4th degree polynomial can have up to 4 intercepts. So it can have 4, 3, 2, 1, and it can have 0 because it'll shoot off to infinities in both the same direction. It can actually be completely graphed above or below the x-axis, so it can have the 0 case. It can have up to 3 turning points, all right, 3 or fewer. All right, it has to have at least 1 turning point, though, because it's got to turn around and go off to the same infinity, all right? So it has to have 1 to 3 turning points. Its end behavior is the same, right? So if my value is positive out front, it's shooting off to positive infinity. So if A is positive, it's shooting off to positive infinity on both sides. If A is negative, it's shooting off to negative infinity on both sides. And because of that, it has to have at least 1 turning point, up to 3. And because of that, it could have no intercepts, right? It could be graphed completely above or below the x-axis. All right, so here's a couple of examples. All right, so the first example, it has 1, 2, 3, 4 x-intercepts. 1, 2, 3 turning points. All right. 2 minimums and a maximum. It has an absolute minimum, right? And then since it's shooting off to positive infinity in both directions, well, my A has to be positive in that case, right? The next example, it has 2 intercepts, 2 x-intercepts, 1 turning point. Right, this is not a turning point. And since it's shooting off to negative infinity, well, that leading term A has to be negative in that case. Next example, it's got 1, 2, 3, 3 x-intercepts, 3 turning points. And since it's shooting off to negative infinity, my A had to be negative in that case. Now, I didn't graph one, but you could see where if I shifted one of these up or down, I'm going to do below, I could have one shaped like this, where it's got 3 turning points, but no x-intercepts, right? 3 turning points. And so that would be an example of where it's graphed completely below the x-axis. Or you could flip it over and graph it completely above the x-axis. All right, next one we're going to look at, we'll stop at 5. The pattern basically continues, but I'm going to stop at 5. 5 is the last one we're going to look at. All right, so fifth degree function, which I'm just going to call it a fifth degree function because that's usually what we say. All right, so a fifth degree function has at most 5 intercepts. So it can have 1 to 5. Has to cross it though because I'm going to positive and negative infinity. So it can't have 0. It has to have 1, 2, 3, 4, 5. Because I have to cross because my infinities are going to shoot off in opposite direction. Maximum of 4 turning points. So it can have none, and you can have 0 in this case, up to 4. All right, 0 to 4 possible, max and mins. The end behavior, well, it behaves like the third degree function. If a is positive, I'm going off to negative infinity when I plug in negative values, so to the left. I'm going off to positive infinity to the right when I plug in positive values. If a is negative, I do the exact opposite. If a is negative, when I plug in negative numbers, I go to positive. And when a is negative, when I plug in negative numbers, or when I plug in positive numbers, it goes negative. It goes to the right, it goes negative. All right, the graph must also cross the axis at least once. So I have at least 1 0. Up to 5 and at least 1. Alright, so here's a couple of examples of fifth degree functions. So this first example, I have 1, 2, 3, 4, 5. 5 x-intercepts, which would be the maximum. 1, 2, 3, 4 turning points, which also would be the maximum. Since it's going off to infinity on the positive side, negative infinity on the negative side, a has to be positive, not negative. Alright, the next function, it's still a fifth degree function. In this case, it would probably not have very many terms. It has 1 x-intercept, right, just that one. No turning points. And a is positive again, because again, it's shooting to positive on the positive side, negative on the negative side. Alright, then the last one. 1, 2, 2 x-intercepts. 1 turning point, right? That's the only, oh no, 2 turning points. Let's count. 1, 2, 2 turning points. And this time it's doing the opposite behavior. Negative infinity, or positive infinity on the negative side. Yeah, positive infinity on the negative side, negative infinity on the positive side. So a was negative in that case. Double check this last one since I kept messing up. Positive on the negative side, negative on the positive side, so a is negative. It has 2 turning points, 2 places it crosses the x-axis. Alright, and so again, the same pattern would continue for 6th degree and beyond. And so I'm just going to stop it there with the 5th degree and do my, again, same summary. The leading term determines the end behavior, whether I'm shooting off to positive infinity, negative infinity on the left and the right side. It's the leading term that tells me that. The degree tells me, it's a little more ambiguous, but it tells me, at least puts me in the ballpark. I can have at most the degree minus 1 turning points. So that's how many max and mins I could have. And the degree tells me how many x-intercepts I could possibly have. I could have at most whatever my degree is, or fewer. If it's odd, I have to have at least 1 x-intercept. If it's even, though, I might have 1, I might not have 1. I could have none in the even case. Alright, so for each of the following polynomial functions, determine the end behavior. And so I'm going to do this in the next video. So I'm going to do this in the next example since this is already a fairly long video. So I'm going to stop there and we'll pick up the exercises in